And good evening, AP Physics students. Welcome to yet another example problem here dealing with work and energy and non-conservative forces. So today we are going to be working on chapter number 6, problem number 48, and working with non-conservative forces and conservation of mechanical energy. So in this problem, it looks like we have a child on a slide, right? And of course, drawing children is one of my favorite things to do, right? Hey, I'm a child, I'm having a slide, I'm having fun, right? And then we get all this information about the child. Like at the beginning, the child starts with an initial height of 3.5 meters. So again, we're assuming, we've got our traditional coordinate system here with, the ground being our 0y and all that kind of stuff. Says the child is about 21.7 kilograms. So on the earth, a kilogram is about 2.2 pounds, or a force of 2.2 pounds. So, 50-pound child seems kind of reasonable. And it says, the child starts at the top of the slide, slides to the bottom, and when they get to the bottom, the child has a speed of 2.2 meters per second. All right. Now, it doesn't explicitly say it in the problem, but from the context, we can gather that the child's initial speed was 0 at the top of the slide. So anyway, and then the question is how much work is done by non-conservative forces? I think the book actually says, how much work is done, how much energy is lost to thermal energy. So again, the work done by the non-conservative force here would be friction. So as the child goes down the ramp, right, the displacement would be down the ramp, friction would be acting back up the ramp, we'd have negative work being done, and that would slow the child down. So what we're going to do here is kind of a big equation. Here's the big idea. So far, we've been working with the idea, if we just go off on the side, so far we've said, hey, mechanical energy is conserved if there's if there's no non-conservative forces acting, right? So potential energy initial plus kinetic energy initial equals kinetic energy final plus potential energy final. And that's great, but it's not always the case, right? In the real world, there are, non-conservative forces. Well, what do non-conservative forces do? They change the amount of mechanical energy in a system. They can make it greater or they can make it less. In this case, it'd be reasonable to think we'd have less kinetic energy because friction's doing negative work. Okay, enough talk though. Let's get down to business. So change in mechanical energy would be EF, final mechanical energy, minus EI. All right. Okay. Well, what kind of mechanical energy would we have at the end here? We'd have no potential energy because we'd be on the ground, right? And we've chosen 0 to be the ground. But we would have some kinetic energy, right? Some 1/2 mvf squared, right? So this would be our final kinetic energy, right? What do we have at the beginning? Well, at the beginning, if we're starting from rest up there, we'd have no kinetic energy, but we would have gravitational potential energy, right? mgy, all right? So, yeah, let's plug this in and see what we get. So we'd get 21.7 times 2.2 squared, right? Minus 21.7 times 9.8 times 3.5, right? And if we plug all of this in and round to significant digits, we would see that the work done by non-conservative forces is equal to negative 690 joules, right? What does the negative sign mean? It means the amount of mechanical energy is going down. That is, I have less kinetic energy at the bottom, than potential energy I had at the top. What happened to that mechanical energy? Well, some of that energy got lost as friction, which would kind of make sense that it'd be negative since there'd be negative work being done. All right, excellent job, physics students. Let's get you something funny here to make you laugh for a reward. All right, and here's our funny cartoon. It's a foxtrot. All right, what do we got going on? Let's see. Oh, he's falling on the treadmill and he says, I suppose friction is one way to lose your Thanksgiving gut. Are you sure this is the slowest setting? Looks like me on a treadmill. Oh my goodness. Boy, that guy's treadmill experience looks pretty rough. Oh, good stuff. All right, nice work, AP Physics students.